So 6.1 and 6.2 starts off by talking about radians and degrees. Radians is just another unit measurement for the opening of a circle similar to degrees. However, radians is constructed with a unit circle, a circle with radius 1, and the radians is just the arc length distance. Now, you can also think of it as the angle measurement because when we work with circles with radius bigger than 1, the arc length is not going to be the same value as your radians unit. We're always going to relate it to the radius 1. So, to convert from degrees to radians, you'll notice that most of our exact radian values will have a pi attached to it. So what we're going to be doing to convert from degrees to radians is we're going to multiply our degrees by pi over 180. And in doing so, we'll have a pi attached to our term, our value. Because if we're multiplying fraction, we multiply straight across. On the contrary, if we're turning radians to degrees, most degree measurements you've ever seen generally talks about some number or whatever, but it does not have a term or a pi attached to that term. You'll say you're rotating 450 degrees. You don't really say you're rotating 450 pi degrees. So we need to get rid of the pi somehow from our radian values. We're going to take our radians, and we can think of it as dividing that amount, but if we're dividing by pi over 180, that is the exact same thing as saying multiplying by 180 over pi. Dividing is just flipping or reciprocating the second term. So, example, if we have 360 degrees, that's the degree measurement of an entire circle. Well, we know it should be 2 pi because if I have a circle with radius 1, the circumference better be 2 pi. The length of the entire circle, arc of the circle, better be 2 pi. So if I multiply this out by pi over 180, I get, this cancels out, I'm left with 2, we get 2 pi. Is our radians amount. You write radians, radian degree. Sometimes you'll see it as rad. Now to go from radians to degrees, let's say I have pi over 4. Well, I need to get rid of that pi, so I need to multiply it by a pi on my denominator. So I need to multiply by something over pi, which is just 180. This is how you'll know or remember what to multiply or divide by when you're dealing with the conversions. Radians, you want to have pi's. Degrees, generally you don't want to. The pi's will cancel out. And then 180 over 4, that's the same thing as saying, I believe that's 45 degrees, I want to say. That is your unit measure converted. Now, arc length is just the distance subtended by your angle with the vertex at the very center. So let's create an angle. Your arc length is going to be this travel distance right here. So if I color code it, it's this orange piece. How long is that orange piece? That's your arc length. So to calculate that, let's call this angle theta. To calculate that, well, you'll notice that this is just a proportion or portion of your entire circle. But we know the entire circle, the length of the entire circle is the circumference, which is 2 pi r. So if I call it this radius 2, let's say this radius is 2, then I can set up a proportion where I have the entire circle. Let's call the entire length of the circle is 2 pi r, which is 2 pi times 2. And then I want to solve for this portion right here. Let's say this is x. If I want to ask you for the arc length, we'll just put x here. Now, we have an angle measurement we can also relate to. I have some theta, and then this is all going to be over with the degrees of whatever my circle is. If you want your answer to be in radians, you put 2 pi because that's what the radius 1. If you want to have your answer in degrees, you use 360 degrees because that's the degree of your entire circle. This is your angles proportion, and this is your length proportion, where the denominator denotes the entire circle and the numerator denotes your portion. So if you do that, you can cross multiply it out. So let's say theta was actually equal to, let's give it an exact value, 20 degrees. Let's say I wanted to calculate that distance x. Well, then I'm just going to be cross multiplying. That's it. If I cross multiply, I have 20 times 2 pi times 2 equals 360x. And if I try to solve this out, well, 2 times 2 is 4, so we get 80 pi equals 360x. X is equal to, and if I want to calculate this even further, what is that? 80 pi over 360, which is going to give me, I can't do math that quickly. Let's see, what is that? 2 over, I don't even know what I divided by. 9? 2 over 9? I might be wrong. So make sure you double check my answer. 2 pi over 9. But that's how we can calculate the distance of that arc length. We can set up a proportion. Now, in your book, they use this formula for you. So you can choose to memorize the formula or not. That's up to you. They say S is equal to R times theta, which is your radius times your angle measurement in the center, where S is arc length. So if you want to write it in your notes, go ahead for that definition. You should already have that definition down, but yes, you can do that. And then if we want to solve for theta, you can do theta equals S over R. I think the proportion teaches you more and shows you more for what you have. So next, we're going to talk about sector area. Sector area. Sector area is just the area in your portion of the circle. So let's say I have an angle. Let's call this theta. Well, sector area, I want to calculate this portion of area within the circle that is created by this angle with the vertex in the center. To calculate this, well, I can use that same proportion idea. 360 degrees. You can use 2 pi as well if you want to, but then your numerator has to be in radians. 360 degrees. Now, instead of the length of the entire circle, we need the area of the entire circle, which is pi r squared. And then I want to solve for that area created by that sector area. So I'm going to put x. And then this is going to be over theta. Let's give some values out where we're going to actually work with radians instead. So let's say you want to work with radians, 2 pi instead. And then I said theta was equal to, let's say, pi halves. You put pi halves over here equals to x. And let's say this is 3. The radius is 3 centimeters. You would do x is over pi 3 squared. 3 centimeters squared. And if you wanted to cross multiply, you have 2 pi x equals, you multiply these together, you get pi squared, or 9 pi squared over 2. Oops, sorry about that. One of the pi's will cancel out once you divide them out, so you have 2x is equal to 9 pi over 2. And then you have 4x equals 9 pi, x is equal to 9 pi over 4. And this is going to be units, centimeters squared. Remember, we're doing area. It's always going to be squared. And you'll notice that when I had 3 centimeters, centimeters times centimeters is centimeters squared. So I should have put that in there to get the idea that it's going to be 9 pi over 4 centimeters squared. That's how we calculate sector area. Now, if you want the formula for that, if you feel better with the formula, we can say the sector area is calculated as 1/2 r squared times theta. All right, but we got those values from the area of the circle itself. It's just a proportion at the end of the day. Now, for the last required content needed for your lesson test, we need to talk about trigonometric functions. So in particular, there's this notation SOHCAHTOA. Now, if you read all the letters out, they pronounce SOHCAHTOA. Now, I can't use that word anymore, so I will refrain from doing so. So have your own mnemonic device to remember these. Now, in particular, these are your trigonometric functions. The S represents sine. The C represents cosine. The T represents tangent. These are all abbreviated as sine, cos, and tan. So these are our functions. If you remember what functions are, they take an input and they spit out an output. The thing is, with these functions, we created these functions so we can relate angle measures and the lengths of sides for triangles. So our inputs and our inputs are going to be angles, say theta, and our outputs are going to be side proportions. So the O represents opposite, the H represents hypotenuse, the A represents adjacent, adjacent over hypotenuse, and then we have opposite over hypotenuse. So what does that mean? If I were to give you a generic right triangle, let's call those A, B, C. A, B, C are the vertex, or you can treat them as the angle that you have for your triangle. So angle A, angle B, angle C. So if I use angle C in particular, let's say we use angle C, I can say the sine, let's give some numbers out, 3, 4, 5. The sine of angle C, so we have to throw in C, boom, is going to be the ratio opposite over hypotenuse. So we have to look at our angle. Now we're going to go at the very center of the vertex, and we're going to shoot it directly across. The side that is opposite to our angle is going to be 4 over our hypotenuse, which is 5, the longest side of the triangle. So we're going to have to do this for each and every single one. If I did it for cosine, I should already have my setups where I have a function, inputs and outputs. Boom. Input, output. My input is the angle measurement. So let's, instead of C, we're going to, let's just use C still. Now, cosine is adjacent over hypotenuse. So the line or the side of the triangle that is adjacent to the angle C is 5 and 3. But which one do you choose? Your hypotenuse is never the adjacent. So it has to be 3 because your hypotenuse is 5. Hypotenuse is never your adjacent, and adjacent is never your hypotenuse when you're working with trigonometric functions. So boom, we're able to calculate these all. And you're also able to calculate the reciprocal functions for stuff such as cosecant, secant, and cotangent. These are just 1 over sine theta, cosine theta, and tangent theta. Use parentheses better. Equals theta. Okay? And when I say reciprocal, we can also just flip the numerator and denominator. When they say 1 divided by something, that literally means you're going to swap the numerator and denominator, if you haven't known that by now from pre-calculus algebra. So, you're able to calculate all of these now. Now, moving forward, we need to be able to solve for side lengths. So what happens if instead I have a triangle, a right triangle in particular, let's say this is 45 degrees, and let's say I need to solve for this. Let's call this x. I need to solve for x, and I have this as 1. Well, I can use some sort of trigonometric identity. I don't know what it is. Let's use something, but it has to relate to the opposite and the hypotenuse, because those are the only things I have to work with. So the opposite and hypotenuse, that's going to be sine. Sine, and remember, we have to write inputs and outputs. Our input is the angle measurement. Now be sure, if you ever use your calculator is in degree mode or radians mode, depending on which angle unit you're working with. If you're working with radians, keep it in radians. If you're working with degrees, keep it in degrees. So now, sine in particular is opposite over hypotenuse, so it's going to be 1 over x. To solve for x, you have to multiply both sides by x, and clearly x cannot be 0, because you can't divide by 0. Now, I cannot do x times 45, so do not make that mistake. We cannot mess with inside of our function. So now I have x sine of 45 degrees is equal to 1. If I solve for x now, x is equal to, this is one singular object, 1 over sine of 45 degrees. You can only mess with the outputs. Don't mess with the inputs. So boom. And if you calculate this out, it turns out that x is exactly equal to square root 2. In your calculator, you'll have a decimal, but the reason why we know it's square root 2, well, it's a 45-degree right triangle. That means this guy has to be 45 degrees. Triangles add up to 180 degrees. 90 plus 45 plus 40 is 180, which means it's an isosceles triangle. So boom. And if you use your Pythagorean theorem, a squared plus b squared equals c squared, you get 1 squared plus 1 squared equals 1 plus 1 is 2. And then we have to square root that all. Messed it up. Then we gotta square root that all. Terrible at this. Boom. Okay? So that's how we get square root 2. A squared plus b squared equals c squared. And in particular, this is a special right triangle. This is called the 45, 45, 90 triangle. If you have a triangle that's 45, 45, 90, or an isosceles right triangle, well, both of the short legs of the triangle are equal because it's an isosceles triangle. They're going to be the same measurement. All you need to know is that this hypotenuse will always be that same measurement, 1 times square root 2. If your short legs were 3, it'll be 3 root 2. If your short leg was 5, your hypotenuse will be 5 root 2. So that's how we're going to work it. If your hypotenuse was, let's say, 6 root 2, then your short legs is 6 by dividing by square root 2. So let's do another one real quick. Let's say I have another right triangle. And this is very important. You need to know how to do this. Let's say we work with pi over 3. This time I'm using radians as my angle measurement. Well, let's say I have square root 3. Well, now we have an angle measurement right here. And we have, I move directly across, opposite. So let's say I want to calculate, I don't know, this guy. Well, what uses opposite and adjacent? The only function we have is going to be tangent. So we're going to do tangent, some input equals my output. Your outputs are always the side proportions. So your input is pi over 3. You have to put your calculator in radians mode if you do this. And then you're going to put in, what am I going to put in? I forgot. Opposite over adjacent, which is square root 3 over x. To solve for x, you multiply both sides by x. So we get x tangent of pi over 3 equals square root 3. You get x is equal to square root 3 over tan of pi over 3. And if you actually calculate that out, it turns out it's actually just 1. So when we have our triangle, we have x equals to 1. Now if you did Pythagorean theorem, 1 squared plus square root 3 squared, this is 1 plus 3, which is equal to 4. And we got to square root that at the very end. A squared plus b squared equals c squared. C squared is equal to 4. So c is equal to 2. And this gives us a new type of special triangle. We have the short leg being equal to 1 distance. Then the hypotenuse is twice the short leg. And the longer leg is square root 3 times the short leg. These are very important rules. So this is the 30, 60, 90 triangle. Where you have 30, 60, and 90 degrees. Where if this is 1, this is square root 3, and this is twice as long as the short leg. The longer leg is square root 3 times as much. Now the last thing we got to talk about is angle of elevation and angle of depression. I'm sure you guys already read the definition of it. However, they are the exact same thing. Angle of depression is the angle formed from the horizontal line in the sky. Boom. This is the angle of depression. Let's say I have a plane. Boom, boom. This is my plane or whatever. I don't know how to draw it. But the plane is going down to maybe a station over here. Right? It's at an angle bearing of 6 degrees. The angle of depression is that. Or whatever. Right? That's your angle of depression. Now if I want to do angle of elevation, however, I can use the same plane problem, but I say the angle elevation from the station right here. These angles are actually congruent from geometry, alternate interior angles. You can check that out. But because they are the same. You can use either or. The only thing that matters is your drawing of your right triangles for these application problems. So when you're working with these, be sure you're able to draw these word problems as triangles for trigonometric functions. That leaves it at that.